Hi everyone, and welcome to this video. You know, if you ever wondered why certain engines absolutely guzzle fuel while others just sip it, or maybe exactly how much usable energy we're literally throwing away just by burning things, well, you're definitely in the right place. Today, we're doing a deep dive and we're going to break down exactly how engineers track down hidden energy waste. We're using some pretty advanced thermodynamics. We're stepping way beyond just the basic first law of energy conservation and plunging straight into the really fascinating realm of chemical exergy. So, here's our game plan for today. We'll start by measuring real-world combustion, then establish the 0 Kelvin baseline. After that, we're gonna model the atmosphere, then we're calculating the chemical exergy, and finally, comparing engines versus reactors. First, let's go through the real-world combustion. In chemistry class, we have learned about perfect, complete combustion where carbon turns into CO2 and hydrogen turns to water. It all looks super clean on paper, but out in the real world, it's almost never that neat. To figure out what actually happens inside a roaring engine or industrial furnace, we have to measure the exhaust. However, the water vapor in that exhaust loves to condense while we're trying to measure it, which throws off the reading. So to get around this, engineers use a clever trick called a dry product analysis, which basically we measure all combustion products except for water. This gives us a reliable dry baseline. But it creates a tricky little puzzle. If you don't know how much water has been produced, how do we find our starting air and fuel? To solve this, we can take a look at the combustion of ethanol, for example. By using known dry exhaust percentage like CO2, CO, and nitrogen, and track down the conservation of mass, we can work backwards to a maze to reconstruct the exact air-to-fuel ratio. Now let's move on to the next part, the 0 Kelvin baseline. So now that we can measure these real-world reactant and products, we need a solid way to track the exact energy states of these shifting molecules. While standard steam tables rely on arbitrary starting points or datums, these don't work on reacting chemical system, where elements are forming entirely new compounds. We need a universal starting line, which brings us to the third law of thermodynamics. It basically tells us that the absolute entropy of a pure crystalline substance is exactly zero at absolute zero, which is 0 Kelvin. The 0K datum becomes our universal anchor. So because of this, we have a beautifully standardized absolute numbers for the entropy of carbon, hydrogen, nitrogen, and oxygen at standard room temperature, or 298 Kelvin. So providing the foundation to evaluate any reacting substance accurately. Now let's move on to the next part, modeling the atmosphere. To find the absolute maximum possible work a system can perform, we must define what it is reacting against. Just as pressurized tank has potential because its pressure is high than the outside atmosphere, the chemical potential works the same way. To calculate the chemical exergy of a fuel, we have to model our ultimate baseline, the Earth atmosphere, known as the exergy reference environment. This models the environment at standard temperature and pressure, consisting roughly of 75.67% nitrogen, 20.35% oxygen, and a small amount of water, vapor, and carbon dioxide. This specific makeup is the dead state. The moment a fuel reaches equilibrium with this mixture, its potential to do work drops to zero. Now let's move on to part number 4. So there's a mistake on this slide. It's actually part number 4, and we'll talk about calculating the chemical exergy. So chemical exergy is the maximum theoretical work a system can perform as it goes from its current state to perfect equilibrium with that reference environment. engineers use a conceptual thought experiment involving a perfectly idealized machine where fuel and atmospheric oxygen enter a reaction happens. The product exits perfectly match the environmental conditions. So this maximum work output is a theoretical ceiling that is impossible for any real-world machine to beat. So to calculate this, we use a thermodynamic property called the Gibbs function of formation. So think of it as an ultimate energetic exchange rate that wraps up enthalpy, temperature, and absolute entropy into one single value, allowing us to compute complex energy balance without losing our minds in the math. So let's move on to point number 5. There's also a mistake on this slide. So let's talk about the engines versus reactors. So even though an internal combustion engine outputting a mechanical power and a steady state reactor that output heats have different goals, both suffer a major energy destruction. The main culprit is the highly irreversible nature of rapid combustion itself. The sheer act of burning fuel instantly destroys a massive chunk of its work potential. In a reactor, exergy is destroyed by rapid oxidation and lost through stray heat transfer through the walls. One of the biggest factors controlling this efficiency is simply how much air we use. So for example, the reactor fed with the exact theoretical amount of air has an exergetic efficiency of 70.3%. But if flooded with 400% theoretical air, the efficiency plummets into 46.3%. This is because excess air dilutes the product, soaks up the heat, and drops the exit temperature, destroying the actual work potential. So we have seen how tracking atoms through dry exhaust leads to absolute entropy, which lets us find the limits of chemical exergy and how parameters like excess air can quietly destroy potential. As we move away from fossil fuels, modeling chemical exergy and tracking this invisible waste will be the blueprint for building a vastly more efficient and sustainable world. Understanding these advanced thermodynamics isn't just about old engines, it's about future green tech and synthetic renewable fuels. And before I end this video, I'd like to give you guys a thoughtful question. I think a question to think about. How can chemical exergy revolutionize green tech in the near future? So that's all from me. Thank you.